the pleasure of having Pietro Caputo from Roma, and he's going to tell us about rapid mixing of Gibbs sampler. Pietro,
okay. Thank you very much, Hubert. Thank you, Claudio, and thanks to all the organizers of this seminar for inviting me to speak here. And I will talk about some recent work on the mixing of Gibbs samplers and some new techniques that emerged in recent years. This will be mostly about recent work with Alexandre Bristiel, Antonio Blanca, Zongchen Chen, Daniel Parisi, and Alistair Sinclair, Stefankovic, and Eric Vigoda. So I will tell you about this general class of Gibbs sampler, and the main tool we will use to analyze this will be something that we call the entropy factorization. Namely, it's basically some functional inequalities that can be used to prove mixing time bounds. And entropy factorization is not a new concept, but it has been used in several results for proving upper bound on mixing time for Glauber dynamics and things like that. But what is new is that somehow we try in this work to kind of give a unified treatment of all these inequalities, and we try to capture in a single concept of factorization all possible inequalities for Gibbs sampler. So you will see what I mean by that. The main topic then will be how do you prove such entropy factorization? And there are essentially three situations where we are able to prove entropy factorization, and this can be summarized with spatial mixing or spectral independence or contractive coupling. So spatial mixing is something that is familiar to all of you, I think, but I will mention that later. Spectral independence is a new concept that emerged a couple of years ago in the work of Anari, Liu, and Obes-Garan, this paper I pointed out here. And this was introduced to attack some problems of high dimensional expanders, and in particular an application to the hardcore model. I will come to that. And contractive coupling is essentially the existence of a contractive Markov chain for the problem at hand, and you will see how that implies the entropy factorization. And that's what I want to discuss later on. And then I would like also to talk about something that I did recently with student Alexandre Bristiel from ENS Lyon about entropy factorization for permutations. So this is a setup where we can prove some very precise estimates with exact constants. So I will try to, I hope I have time to say something about that and the implications for some combinatorial problems. So the main references I will refer to are these papers here we wrote with the co-authors I mentioned earlier. And as I said, a key ingredient will be the spectral independence that was introduced by Anari, Liu, and Obes-Garan 2 years ago. And also another important paper is this by Chen, Liu, and Vigoda, who realized how to use spectral independence to prove mixing time bounds for Glauber dynamics. Okay, so please stop me if you have any question, and if you cannot hear or anything, please don't hesitate to stop. Let me briefly introduce the setup of this talk. It will be the main objects will be Gibbs measures. Gibbs measure here is let's look at it as a spin system on a graph G. So we are given a graph, finite graph with maximum degree delta, and this parameter delta will be the constant we will derive will be depending on such delta. And Gibbs measure will be, to simplify the setup, let's just think of spins as being, each spin as being either one of q possible values. So some integer q is given. And the Potts model is familiar to all of you, is given by the following expression. So it's a probability measure that is proportional to the exponential of beta times the number of monochromatic edges. So monochromatic edges where the set of edges where the spins at the endpoints are equal. And beta is just a real number. If beta is non-negative, this is the ferromagnetic Potts model. Okay, and q is just some integer larger or equal to. When q is equal to 2, this is the Ising model. For simplicity, I'm taking zero external field, but there is no problem in discussing also systems with external fields. Okay, so another model that you can deal with these techniques is the Q colorings. Namely, you are given Q possible values for the spin at every site, and you forbid you forbid to have two at the endpoint of a given edge to have two equal colors, two equal spins. So the measure mu is just the uniform measure over all such proper Q colorings. And another Gibbs measure that can be studied is a classical model is the hardcore model. So you have two values of the spin here, and you give you call I the set of independent sets of the graph G. This is the equivalent to saying all spin configuration such that no edge has two endpoints where both spins are equal to 1. Okay, and so then you give a weight that is proportional to lambda to the power of the cardinality of such an independent set. And lambda is a positive number that is called the fugacity of the model. So these are classical statistical mechanics model, and an important problem is the possibility of sampling from such models. And a classical way of sampling is by using Markov chains. So let's talk about the Gibbs samplers. The classical sampler are given as follows. Let me introduce this notation: mu lambda tau for the conditional distribution of our Gibbs measure, conditioned on having spins equal to tau outside a given region lambda of our graph. Okay, so this is mu lambda tau, and lambda is just any subset of the vertices. Tau is often called a boundary condition or a pinning for the Gibbs measure. So for any function f, we write the conditional expectation as this function here, which is the function that gives the value mu lambda, the expected value of f according to mu lambda when you specify the boundary condition outside of lambda. Okay, so with this notation, a general formulation of a Gibbs sampler is as follows. Suppose you are given weights alpha lambda. So for each subset lambda of your set of vertices, you have some probability alpha lambda, and so that all these alpha lambda will sum up to 1. Okay, so that then you consider the Markov chain that at every step picks a set lambda with probability alpha lambda, and then you replace the configuration of spins sigma lambda in that region according with a sample from the Gibbs conditional distribution mu lambda given whatever you had in the current configuration outside of lambda. So a compact way of writing this is a stochastic operator, which is just sum over lambda, alpha lambda, and mu lambda f, which is the conditional expectation. And this will be called the block dynamics associated to the weights alpha, or alpha weighted block dynamics. That's just a compact way of writing a general block dynamics. Because up to now, these alpha lambdas are completely arbitrary. Okay, so classical examples are the Glauber dynamics, when you take the alpha lambda to be all of size, the lambda to be all of size 1. So that means you pick at random a vertex, uniformly at random, and you take the block dynamics that just updates the single vertex every time. Okay, so that's just the standard Glauber dynamics. And this is where most of the results have been focused so far in the literature. And one of the main motivation for this work I'm talking about was actually to be able to go beyond such dynamics and being able to study also some non-local dynamics, because Glauber dynamics is very local, and you could also look at other block dynamics that are very local in the sense that you update a block that is of a finite size when the graph grows, of a bounded size. Instead, we wanted to understand also some block dynamics that are non-local. So for instance, you update, I don't know, so if you have a bipartite graph like ZD, you could update all the even sites in one step, and say with probability a half, and all the odd sites in one step with probability a half. That would be a choice of alpha lambda, so that alpha on the odd sides is 1/2 and alpha on the even sides is 1/2. And these are much less studied dynamics in the literature, and they are somehow not easy to analyze with the tools that have been developed so far for the Glauber dynamics. So one of the motivation of this work was to be able to develop some tools that allow you to treat general dynamics in this sense. Another interesting fact is that although it does not follow immediately in this category, there are very interesting non-local dynamics like the Swendsen-Wang dynamics for the Potts model, and these can be thought of as a non-local block dynamics in a slightly more general spin space. So I will maybe mention something about that. So our technique will allow us to analyze these dynamics as well, like Swendsen-Wang dynamics. So that's the main motivation. Okay, just one observation: this P alpha is always a reversible Markov chain, and it converges to the Gibbs measure as soon as you have some irreducibility condition. That mainly here it reduces to just requiring that every vertex has a positive probability of being picked in one of the sets which are chosen with the probability alpha lambda. So there is general expression for the Dirichlet form, namely the quadratic form associated to the Laplacian of this Markov chain. And this has an expression in terms of covariances, local covariances, as this form. So are there any questions so far? Do you want me to say something more about the setup, or? Okay. So I guess we can go on, and let me tell you some standard stuff about mixing time, just to make sure we speak the same language here. For a Markov chain with a stochastic matrix P and stationary distribution mu, you look at the mixing time T mix of P And for simplicity here, we just talk about discrete time Markov chains, but nothing is changing if we do continuous time. So for the discrete time, you take an integer t and look at the distribution after t steps of the Markov chain. This is given by this expression, p to the power t sigma dot. And then you compare this distribution to the equilibrium distribution. And in total variation distance, this should be at most 1/4, say. 1/4 is just a parameter that is less than 1, that is conventionally chosen in this case. And you do this uniformly in the initial condition. So it has to be, your distribution must be close to equilibrium independently of where you started from, after so many steps, after this number of steps. Now, another standard quantity is the entropy. The entropy functional for a function, for a Gibbs measure mu, associates to a function f this quantity here, the expected value of f log of f over mu f. And this is related, it coincides with the relative entropy of the measure f mu, namely the measure with density f with respect to mu, and relative entropy with respect to mu when the expected value of f is 1. So when f is really a density, this is just the relative entropy, just to recall the relation here. And it's important also to have a local version of the entropy, namely when you take, instead of the measure mu, you take your conditional distribution mu lambda, as we have seen before. Okay, so this entropy lambda f is actually a function that when you give the value of the boundary condition outside of lambda, this gives you the value of this relative entropy. Okay. Now, it's a standard fact relating total variation to relative entropy, namely the Pinsker inequality. And this can be used to prove the following lemma. So this is a lemma that is easy to prove once you have the Pinsker inequality. Namely, if your Markov chain contracts the relative entropy in this sense, namely that entropy of P of f is less equal than 1 minus delta entropy of f, this for any non-negative function f, then the mixing time is at most a constant, say 4 times 1 over delta, which is the parameter of the contraction. And then you have this log of 1 over mu star, where mu star is the minimum possible value of your Gibbs measure. And it's important that in cases where your Gibbs measure has hard constraints, like in the coloring or the hardcore, you are allowed here to take the minimum positive value. So there is no risk of taking 0 here. Okay, so that this lemma here will be the main tool that one uses to prove upper bounds on mixing times when you have a contraction of entropy. So what we will do morally will be to prove inequalities that guarantee that you have a contraction of entropy, which then by this lemma will give you an upper bound on the mixing time. And for those of you who are familiar with the log Sobolev inequalities, let me just say that this entropy contraction is can be seen as a discrete time version of the so-called modified log Sobolev inequality. So in discrete time, this is the natural object you want to look at. But whatever I will say will also prove the corresponding continuous time entropy inequality, namely the modified log-Sobolev inequality. So if you prefer, you could think of that we are actually proving a modified log-Sobolev inequality. Another observation is that in all the models I mentioned above, this term log of 1/mu star is always of order log n, and this will produce in most cases an optimal mixing time bound. If you're able to prove, say that this delta is uniformly positive for the models we discussed, this will provide a tight upper bound, namely an upper bound that is sharp up to a constant factor. So are there any questions so far? Okay, then let's come to the entropy factorization I wanted to introduce. So we introduced this general notion that we call block factorization. And this definition is as follows. You take a constant C, and you say that block factorization with constant C holds if for all weights alpha, so this inequality must hold regardless of the choice of the alpha, and for all functions f, you have the inequality that I wrote here, namely that the full entropy of f multiplied by gamma of alpha is at most C times the weighted sum with weights alpha lambda of the expected value of the local entropies on lambda. And this gamma alpha is just the minimum over vertices of the total weight that covers one vertex. So this gamma alpha is essentially the minimum probability that a vertex is chosen, is updated in a step of your Markov chain. So with my student Parisi, we introduced this notion, and let's see why this is interesting. So I hope the inequality makes sense. If you have doubts about the meaning of the inequality, please let me know. Okay, I cannot see everybody. Let me check if okay, yeah. Okay, so first observation is that when mu is a product measure, namely you are considering independent spins, so the trivial case, then this inequality always holds with a constant equal to 1. And so this explains why we are normalizing things with this gamma alpha, because this gamma alpha is really what you have to put here to obtain constant 1 when you have independent random variables. Okay, and this is a fact that is an immediate consequence of the well-known Scherrer inequality for the Shannon entropy of arbitrary random variables. Okay. Another observation is that if you take the Glauber weights, namely you take uniformly at random a single vertex, then what you obtain, then this inequality becomes what is sometimes called the approximate tensorization inequality. And this approximate tensorization in the setup I'm discussing here is actually equivalent to the log-Sobolev inequality for Glauber dynamics. And this has been studied for a long time. And starting with the early 90s, there have been very strong results by Strucken, Zigarlinsky, Martinelli Olivieri, Yao, and Chesi, and several others. Let me also point out that these results were mostly establishing such inequalities for ZD spin systems. So when the graph is a subset of ZD and under the strong spatial mixing assumption. And yeah, for generic graph, these techniques were not always suitable to prove the approximate tensorization, but there were a number of other papers that dealt with that. And also interesting that more recently there were papers that dealt with these inequalities under the assumption that there is a negative dependence. There's various notions of negative dependence or log concavity, and there's some interesting results establishing this type of inequalities under such assumption. And even more recently, this is a topic that is receiving a lot of attention recently. There has been a very interesting development by Anari and his group at Stanford, and by Eldan and Chen. So there are new techniques that have been used also to attack more difficult problems, for instance, the spin glass problem, to prove an approximate tensorization for high temperature Sherrington-Kirkpatrick model. There have been interesting progress there. So this is a very well studied problem, this approximate tensorization. Okay, so here we want to focus on the general formulation that I gave up here, namely the block factorization with a constant C, which of course will imply the approximate tensorization, but it's a much more general statement in a sense. Any question? Okay. Okay, so why is this interesting for the mixing times of the Gibbs sampler? This is a very simple lemma, so I'm not going to. It's a two-line proof really. It just says that if you have the block factorization with constant C, then for arbitrary weights alpha, you will have a contraction of the relative entropy for the alpha weighted block dynamics, and the constant delta is just given by the gamma alpha over C. So C is the constant of the block factorization, and gamma alpha is the minimum probability of a vertex being updated in a single step. And once you have this with the Pinsker inequality that I mentioned above, you have also an upper bound on the mixing of the general block dynamics. So general block dynamics will have this upper bound as soon as you have a constant C in the block factorization. So that will be the lemma that you use when you want to get to mixing time upper bounds from block factorization of entropy. Okay, so that's a simple thing, and
so this means that when you're looking for this block factorization, you always aim at a constant that does not depend on n, or?
Okay, yeah, that's a good point. I will actually mention a problem here, that in this work with Bristiel, we actually look at the factorization for permutations, and in that case, you will not be able to get a constant C that is independent of n, but you will actually be able to compute exactly the constant C, and its dependence on n will be optimal. So actually, no, the answer is that if you're able to catch a good dependence on n, that's very good. So this C is not always necessarily independent of n in what we try to prove. Yeah.
The dynamics is reversed.
Other question?
Yes. So are you assuming your dynamics to be reversible?
Yes, yes. This P alpha is always reversible. Is the block dynamics? Yeah. This is, you pick at random a region lambda with probability alpha lambda, and you update with a heat bath in that region. So that's always reversible because you do conditional expectation. Okay. Any other question? Okay, so then the question is, I guess I convinced you that block factorization is interesting, but when can you prove it? So the question is, when can you say anything about that? And there are three sets of results that are somehow in increasing level of generality here. So the first thing we understood with my student Daniel was that if you have a spin system on ZD and you have a strong spatial mixing assumption, then we are able to prove block factorization with a constant C that is independent of everything. So in this case, the constant C is really a constant. Another thing that we understood later on when we learned about this spectral independence notion that I mentioned is that actually you can do a much more general statement, namely, as soon as your system has a spectral independence, and I will tell you what that means really, then on every graph, you will get a block factorization with a constant C that actually only depends on the maximum degree of the graph and on the constant that are involved in the definition of the spectral independence. And then we understood a more general fact, namely that actually it is sufficient to have a weak statement about the existence of a contractive coupling, and then on general graph for general spin system, you will get again the block factorization, because actually under this assumption you will be able to prove the spectral independence, and so you will be able to use the previous result. So I can tell you briefly these three results, namely that strong spatial mixing implies block factorization for ZD, and that spectral independence implies block factorization on general graphs, and also that the existence of a contractive coupling implies the same. So let me be more specific here. So for any spin system on ZD, let me be quick in the definition of strong spatial mixing. So you say that the system satisfies strong spatial mixing if essentially a discrepancy in the boundary of your spin system, in the boundary condition, is propagated inside a region with probability that is exponentially small in the distance of your discrepancy to the region you're interested in. So this is a notion of exponential decay of correlation. It's a strong version of exponential decay of correlation. And under this assumption, you can prove that the block factorization holds with a constant C that is independent of n and the boundary conditions. And the idea is that, of course, you would like to use the kind of results that were used in this series of pioneering papers about the log-Sobolev inequality. They established that if you have strong mixing, then you can prove the log-Sobolev inequality for the Glauber dynamics. But as I said, there is a problem because all these results use in a very strong way the fact that the Glauber dynamics is local, namely that when you sum up the pieces of your Dirichlet form, you reconstruct your global Dirichlet form. Whereas here, the Dirichlet form cannot be broken into small pieces. So you cannot do you cannot repeat the same recursive arguments that were done there. So we found that a way to get the full factorization is to first reduce to proving a bipartite factorization. Namely, you break your system into even and odd vertices, and you do with probability a half all the even and with probability a half all the odd vertices. And there is a trick that allows you to go from this to an arbitrary block dynamics. So the first thing to realize is that it is essentially sufficient to prove this bipartite factorization. And then you play with a somehow modified recursive strategy, not the same that were used for the Glauber dynamics. And for this, you prove even odd factorization. So there is no additive, there is no simple additive structure here. So there is a bit of work to do. But once you understand how to do a modified recursive strategy, then you can prove this. So that's what we did in this first theorem. And then we realized also that actually similar ideas could be used to treat the Swendsen-Wang dynamics. So Swendsen-Wang dynamics is a process where you update entire clusters at every step. So it could modify an entire region which has size of order n at each step. So it's a very non-local dynamics. But with the similar ideas, you could prove the following result, which is new, and it says that as soon as you have strong spatial mixing, the Swendsen-Wang dynamics for ferromagnetic POTS models has an optimal mixing bound of order log n, and this holds on any ZD as soon as you have for any dimension as soon as you have strong mixing. And in particular for the dimension 2, this can go all the way to critical point, because it's known that strong mixing goes to critical point in dimension 2 for these models. And again, the idea is to try to prove a factorization here, but this time you want to do a factorization into the spin and edge variables, because for Swendsen-Wang dynamics, it is very useful to consider the Edwards-Sokal coupling of the POTS model. And this introduces edge variables. And once you have the edge variables, you can sample the spins by just giving uniformly at random the colors to every cluster obtained in the edge variable. So maybe I will not be too detailed here, but the key idea is to prove instead of the even odd factorization that I mentioned here the key idea is to prove a spin edge factorization, namely in this enlarged probability space where you have both spins and edges, then you prove that there is that if you condition on a spin or condition on edges, then you have this factorization of entropy. And the way we prove this spin edge factorization is by lifting essentially the even odd factorization that we have in this previous theorem. So with some work, you can go from the even odd factorization to the spin edge factorization. And you can also prove a lower bound. So this is really an optimal mixing time bound, up to constant. So this were the, yep.
In this result, is bipartite very important, or if you're tripartite, this would? Like, if does it work for triangular lattice?
Yes, yes. So when we wrote this paper, we did not think about that. We were just thinking about ZD. But then we realized in further work, we realized that you can do this for any graph, except that what you will have is that this constant will depend on the maximum degree of the graph. And the point is that any graph with, say, maximum degree delta will have a multipartite representation with at most delta plus 1 parts. So once you have a multipartite representation, you can try to prove, instead of a bipartite factorization, you can try to prove a multipartite factorization. And once you have that, you can do the spin edge factorization. So the trick is to go to a not just bipartite, any multipartite will work, but then the number of parts will show up in the constants here. Okay. Okay, so let me see what I can tell you here about the spectral independence, or yeah. So maybe I will be a bit quick on these, but let me tell you what is the spectral independence. So this was introduced by Anari, Liu, and Oves Garan, as I said, to have an efficient way of analyzing the Glauber dynamics for the hardcore gas in the uniqueness regime. So what does that say? So the notion is quite simple. It's just consider the so-called influence matrix. Namely, you take your measure and you look at given vertex X and spin A and vertex Y and spin B, you say, what is the probability that at Y I see B, given that at X I see A? And then you compare it to the probability of just seeing B at Y, unconditional. This defines a matrix in a space where you consider both vertices and spin values. And the eigenvalues of this matrix are real, because for some reversibility that you can easily check, the eigenvalues are real. And there is a maximal eigenvalue, and you say that the system is eta spectrally independent if the maximum eigenvalue is at most eta. That's the notion of spectral independence. And eta has to be non-negative, because if you take, because the eigenvalue 0 is always present in this matrix. So the important thing is that this has to be at most eta for all possible pinnings, namely whatever boundary conditions you put around here, you always have this bound. Okay, so that's the notion of eta spectral independence. And the main theorem in the Allo paper is that if you're eta spectral independence for some eta of order 1, then the Glauber dynamics has a polynomial mixing time. And this is a nice result that uses a powerful recursive approach to prove the spectral gap of the Glauber dynamics. This is something that they call the local to global approach that was developed in the setup, abstract setup of matroid and simplicial complexes in recent work on high dimensional expanders. But it is not very different from the recursive techniques that were used already in the 90s in the work of Yao and the other authors I mentioned. So it's actually just a way of rephrasing those techniques, but it has a slightly more powerful twist, I would say. So there is, they were able to take advantage in a more powerful way of all possible ways of averaging the recursion. And this matrix comes out naturally in that approach. So it's kind of interesting that there was some improvement with this in the introduction of this notion of spectral independence. So the main result we have is that if your system is eta spectral independent for some eta of order 1, then the general block factorization holds with the constant c that depends on this parameter eta. So all weighted, all alpha weighted block dynamics have this mixing time bound. And also all the Swendsen-Wang, I mean, all the Potts model have Swendsen-Wang dynamics with mixing order log n, as soon as you have an eta spectral independent system. Okay. And for Glauber dynamics, this was first observed in Chen, Liu, and Vigoda. But for arbitrary blocks and Swendsen-Wang dynamics, there is more work to do because, again, as I said earlier, there is no local structure that allows you to use this recursive approach. So there is a technical step in this recursive approach. You cannot just reconstruct the Dirichlet forms or the entropy functionals by looking at local pieces. You have to do some more global operation. And with the techniques that we have developed for this for the ZD model, by extending those, you could essentially go to the arbitrary block and Swendsen-Wang. So yeah, here there is this discussion about the multipartite, but maybe I will skip that since I already mentioned this this thing. Maybe just a quick slide on the strength and weakness of this approach. So the strength is that, as you see, you prove tight bounds, and in some cases you are able to go all the way up to the uniqueness threshold. Namely, these bounds, for instance, consider the hardcore gas. This spectral independence of order 1 actually holds up to the uniqueness threshold, which is known to be a complexity, a hard complexity threshold. Namely, above that, the computation of the partition function is known to be an NP hard problem. So you cannot, so it's really the optimal threshold that you can reach if you're interested in arbitrary graphs. And a similar discussion can be done for Swendsen-Wang and Ising model, where you can go up to the tree-uniqueness threshold, which is the optimal you can reach with if you're looking at arbitrary graph. And this result was known for Glauber by Mossel and Sly, but it was not known for Swendsen-Wang or general block dynamics. So there are some strong. It is quite powerful, this approach. On the other hand, the weakness is that you do require bounded degree, as I said, in various occasions. And for instance, to get this multipartite picture, you do require bounded degree. And also another restriction is that you require a minimal probability bound on the single site marginals. Because when you treat entropy, if you want to use spectral independence to obtain results on entropy, you have to introduce this minimal probability for a single site. And this is not good, of course, if you're dealing with unbounded or continuous spins. So these techniques will not give you anything interesting if you're doing unbounded or continuous spins, spin systems. Okay. Are there any questions? Okay, good. So one thing that I mentioned earlier is that these things can be done also under a weaker assumption, namely the existence of a contractive coupling for our Markov chain. And that the idea is that one can prove that the existence of a contractive coupling allows you to obtain spectral independence. So then once you have spectral independence, we have seen that you get all these results. So let me just say very quickly what this contractive coupling is, and let me give you one simplified result that kind of explains the type of things one can do. So suppose you consider the expected distance after one step of the Markov chain. So this W1 P sigma prime is the Wasserstein-1 distance for one step of the Markov chain when you start at two different configurations. And the classical notion of contraction of coupling in the literature, sometimes it's called the Olivier-Ricci curvature condition, says that you have this curvature with parameter rho between 0 and 1 if you have a contraction of this Wasserstein-1 distance in one step of the chain. And here the contraction is measured with respect to the metric given by the Hamming distance. So when you consider the number of discrepancies in the spin configuration. And so we say that there exists a contractive coupling when this holds for the Markov chain P. Now the theorem is that if the Glauber dynamics has a curvature rho, namely you can prove contraction of this type for the Glauber dynamics, then you obtain spectral independence. And the spectral independence is with a constant eta equal to 2 over rho times n. So to understand the scaling here, think of Glauber dynamics, which typically has a rho of order 1 over n, because you pick every vertex with probability 1 over n. Then you take, this gives you an eta of order 1, if that's the case. And so, in particular, by our previous results, this gives you also block factorization. So the interest of this theorem is that you can relate an algebraic condition like spectral independence to a purely coupling condition like this curvature. So this is an interesting result that we proved that was kind of new in the literature, because there are very it's rare to find condition of the sort that results of the sort that coupling implies entropy inequalities like in this setup. What is also even more interesting is that this theorem is just a very simplified version of a more general result that tells you that actually you can have as soon as you have a contractive coupling for an arbitrary Markov chain that has some local property, it doesn't have to be the Glauber dynamics. It can be a much more general Markov chain. And also the metric that you have here can be a much more general metric. So this theorem continues to hold. So that allowed us to prove various things that were not known before, because you can establish just some weak coupling state. So that's all I wanted to say maybe about this coupling things. And of course, if you have questions, I'm happy to discuss this. So maybe if I have 5 minutes more, I will tell you about the entropy factorization for permutations. And this is something that I mentioned before by answering Hubert's question, namely that you can ask yourself what is the best constant that you can put in this block factorization when you deal with the uniform distribution over permutations. And what we did is we were not able to consider arbitrary block factorization. Namely, we were not able to consider arbitrary alpha. That would be actually an interesting question. But what we did is we were able to compute exactly the constant when you consider block factorization with, where alpha is a uniformly chosen block of size L, and this for any L. So you take any L and you take alpha to be a uniformly random block of size L. In that case, it's easy to compute the gamma alpha is just L over N. And so your inequality would be gamma alpha, this L over N here. Entropy of F is bounded by, this is the alpha here. So the constant C is this K and L. And we compute exactly the K and L. It's given by this quantity. It's L log N factorial divided by N log L factorial. And one thing that you can also check is that the unique extremal functions for this inequality are the Dirac masses, or multiples of Dirac masses. Okay, so what does this say? Let's see. Okay, so if L equal 1, this would be the Glauber dynamics, but for this problem, Glauber dynamics is trivial, because if you fix all the labels except 1, then the permutation is completely determined. So there is nothing interesting at L equal 1 here. On the other hand, of course, L equal N is also trivial, because that when you put everything in one step to equilibrium, so the constant is going to be 1. But for L intermediate values, it's non-trivial to prove this thing. And the way we prove it is by adapting the classical martingale recursive approach that was used in the proof of logarithmic Sobolev and modified logarithmic Sobolev for random transpositions. And these were in work of Li and Yao and Goel, Gu and Quastel. But the interesting thing here is that in these log Sobolev works, you cannot compute exactly the constant. So you get it, you get a tight bound up to constant, but you don't know the exact value of the constant. Instead, for this inequality here, for block factorization, you can compute exactly the constant, and this is really an exact computation. And so, in some sense, this suggests that this type of factorization inequality is a more fundamental object than the log Sobolev in this kind of setup. So it really allows you to compute exactly the constant. And I will tell you in just maybe the last slide what one application of this that we were quite happy with is that you can prove thanks to this inequality, thanks to the fact that you know the exact constant, you can establish an upper bound on the permanent of an arbitrary matrix A with non-negative entries. And this proves a conjecture of Karlen Liebenloss of around 20 years ago, and independently formulated also by Samorod-Nitsky a little bit later. And the conjecture is the following. So take the permanent of the matrix A. So this is just the sum over all permutation and the product of the elements I, sigma I. And the bound you get is the following. For any P larger or equal 1, the permanent is upper bounded by the max of 1 and factorial over n to the n over P. And then you have the product of the P norms, of the LP norms of the rows of the matrix. And you also understand what are all the extremal matrices all the matrices that saturate this inequality. So in particular, it's a sharp. This bound is attained at say the all one matrix or the identity matrix. And so, okay, upper bounds of this type of determinants are very well studied in the literature, combinatorics and computer science, because they provide algorithms to compute the permanent, and computing the permanent is a well-known difficult problem. So let me just say that this inequality that you get, that the proof of that conjecture is actually an immediate consequence of the inequality we proved about the factorization, because a dual version of the factorization is a statement about subadditivity of entropy, and the subadditivity is well known to be equivalent to a family of inequalities about the expected value of products of functions, and such things can be turned into this permanent inequality. I will not give you the details because I have no time, but it's quite a straightforward step. Once you have the exact constant, it's quite a straightforward step to get to the permanent inequality. So I just wanted to point out that once you have access to exact constants, you can do something interesting with these inequalities. So maybe I should stop here, and I'm happy to take questions, of course.
Thank you, Pietro.
Thank you.
How do we have access to the question? Shang-Jie, you can. Do you want to ask your question?
Yes, Pietro. Could I ask that does the product factorization imply some low bound on the spectral gap?
Yes. Okay. Yes. So these inequalities about entropy are always stronger than the corresponding inequalities about spectral gap. Let me just tell you quickly why. The point is that when you define this entropy factorization, you have this inequality about entropy functionals, and the spectral gap would correspond to the same inequality when you replace entropy by variance. And if you replace the variance here, you get the Dirichlet form of the heat bath block dynamics. And if you replace the variance here, you get the variance of the function. So that would give you spectral gap gamma alpha over C. And so as soon as you have, so in particular in this lemma, we have seen that if you have entropy contraction with this constant, then the same argument would give you spectral gap with this constant. So another way to put it is that if you linearize the function f by taking f equal to 1 plus epsilon, some other function g, and taking epsilon to 0, this will give you to the dominant order in epsilon, this would give you the spectral gap inequality. So the answer, yes, this thing implies the spectral gap inequality with the same constants.
Okay, thank you.
Yep.
About the fact that contractive inequality implies your bound on the entropy. Does it also work if the contraction bound you have is not exactly about the Wasserstein-1 distance, but like a weighted distance on spins? I mean, if you have a contraction on something, can you get something?
Yeah, that's an interesting. We do need a Wasserstein distance because the whole proof is based on writing this maximum eigenvalue of the influence matrix in terms of a difference of an observable between two different measures. So it's the Wasserstein distance. It's difficult to avoid. What could be relaxed is what you want to contract, namely one thing that we understood is that you could do very, very general Markov chains. So you can play much more with the Markov chain rather than the norm you are looking at. And the statement the general statement that we could do is that if you have a Markov chain associated with mu, namely that has the only request is that it has mu as invariant measure, and you have a family for all pinnings, namely for all boundary conditions, you get the Markov chains associated to the conditional distribution, and you say that it is phi local if when you modify the one vertex of the boundary condition, the Wasserstein is at most Wasserstein 1 is at most phi for the Markov chain that starts with the same sigma. So you take a different boundary condition, but you start with the same sigma. This has to be bounded by some constant. And then, but other than this, the choice of your P is really arbitrary. So this is just saying that your discrepancy propagates by a finite amount, essentially. And then the theorem is that if your family is phi local and these chains have curvature rho, so you need Wasserstein 1, then you have the spectral independence with a constant that depends on phi and rho. So that's the most general formulation we were able to do. We were not able to get a more general weighted Wasserstein, but that could be maybe investigated. We haven't really tried too much, maybe.
Yeah, I was thinking about the kind of contraction you can get for monotonic functions to get bounds on the spectral gaps. If you could get something similar there, but Log-Sobolev is always more difficult than spectral.
Okay, but that corresponds to putting weights on your metric, right? So so you can do that. That's just replacing the Hamming distance with a weighted Hamming distance. So you can do that. Yeah, we can do weighted Hamming distance. That's not a problem. What we cannot do is relax the Wasserstein 1 to, well, I don't know if you have in mind some other Wasserstein, but yeah, but putting weights on the Hamming distance, this is okay. Yeah, that works.
So I have maybe two questions. And so the first one is a little bit conceptual, is what is the advantage from I don't know, maybe a simulation point of view of using block dynamics instead of global dynamics? Because in principle, if you use block dynamics with big blocks, you have to simulate the block, and that gets rid to some computational cost, right? So I don't know if there are what is your view on that point?
Yes. So okay, the one thing that we started with some years ago, we wanted to understand systematic scan dynamics, where you give a scan pattern, namely you give a sequence, a fixed sequence of spins, and you want to update in one step, you update all of the spins in that sequence, in that order. Okay, that's typical dynamics that is actually used in practice more than the Glauber dynamics. So people use a lot systematic scan. The problem is that systematic scan is much harder to analyze because the sequence you are given is fixed. And there are some results, but under very restrictive assumptions. So we wanted to understand that. And so one thing, actually, for that completely general problem, we do not have an answer. I don't know how to do that general problem. But one thing you could understand is if your systematic scan is, say, the sequence is, first you do all the even sites and then you do all the odd sites. So suppose your graph is bipartite, say. Then you can do that with our technique, because that's almost like doing with probability half the even and with probability half the odd. So in that sense, there is an advantage in doing this like all the even and all the odd, because that gives you an analysis of the systematic scan when you choose the sequence to be all even and then all odd, say. So that's one way to put it. Another way is consider the Swendsen-Wang. The Swendsen-Wang is quite efficient even at low temperature for the Ising model or Potts model, and that I mean that is a clear advantage when you study non-local. I mean, the Swendsen-Wang is a clear advantage over, say, Glauber dynamics in low temperature or even at high temperature. But in that case, as you said, the computational cost of one step could be comparable to that of many single steps. So yeah, of course there is a balance, but I guess the low temperature is a strong motivation for studying the Swendsen-Wang.
So another question. So you mentioned this curvature bigger than zero. So, but for example, when you take the pots with the external field, sometimes curvature is negative. And so
yes.
So what happens there?
Yes. Yeah, the pots is more complicated. Even like for the Ising model, say the ferromagnetic Ising, you can go all the way to critical and get a contractive coupling. But for pots, this is not known, and even without external field, it's not known. But then, as you say, when you start playing with external field, maybe things get even more complicated. So I guess we don't know. We don't know in these cases what you could be doing. I mean, if you're in a regime where you still expect rapid mixing, then maybe yeah, some other technique has to be understood. Maybe but if you expect some decay of correlation, maybe you can play with some other type of recursion. I don't know. I haven't tried that.
So one more. Now is the last question, okay? So sometimes it's interesting to tackle these mixing questions, but not in the classical sense we are used to, on which we thought we define the mixing as the worst case scenario. But sometimes I don't know, for some reason you know that your configuration has to be like density 1/2, so you put yourself in density 1/2 with, let's say, Bernoulli.
Mm-hmm.
So these techniques, can you say something about this type of situations with these techniques?
Yeah, no, that would be very interesting. But I think in general, these functional inequality techniques are difficult to use to attack this type of problem. But yeah, I don't think there is a general recipe to do that with these techniques. But maybe in some special cases one could try to develop some ideas. But yeah, I don't have a general application of that.
Okay. Yes, thank you.
Yeah, thank you.
Okay, so I think we can thank Pietro again.
Thank you.
It was very nice to hear you.
Yeah, I hope you guys are doing well. Take care.